Hello friends, in this video let's look at another interesting mechanics problem. So we are given a hemispherical bowl of radius r rotating about its axis of symmetry. So this is the bowl whose radius is r and this is rotating about its axis of symmetry. There is a small block at a position where radius is at the angle theta. So this is the block and this is the angle theta. This radius makes angle theta with the vertical axis. Coefficient of friction between the bowl and the block is mu. So the coefficient of friction at this place is mu. We have to find the range of the angular speed so that the block does not slip in the bowl. Let's analyze this. Let's understand the motion of the ball, or the block. This is your bowl. This is the block. This angle is theta. The radius is r. So now if the g is downwards, now if the sphere is rotating like this at angular speed omega, then obviously the block is making a circular motion like this of angular speed omega with radius at this point, and the value of the radius is r sine theta. So the block is making a circular motion with angular speed omega and radius r sine theta. Now let's look at the frictional forces acting on the block. We'll switch to the frame of reference of the block itself, which is a non-inertial frame of reference. So in order to, what that means is that in order to apply Newton's laws, we'll have to invent some pseudo forces, essentially centrifugal force, since the block is making uniform circular motion. All right, so let's understand a little bit about the frictional forces acting on the block. So this is the center of the sphere. This is the radius and this is the block of mass, let's say m. This is a tangential surface to the sphere at the point where the block touches the bowl. So the normal reaction essentially is going to be in this direction. And the other forces acting on the block are, there is mg, weight, which is downwards. And since the circular motion is around this center, so in the frame of reference of the block, which is non-inertial, there is another force here, which is the centrifugal force. So this is r sine theta, and the angular speed is omega. So this force is m omega square r sine theta. Now, let's think about the frictional forces. The weight of the block has the tendency to make it slip in this direction. Hence, there is a frictional force to oppose that in this direction. Let's call it friction due to weight. Similarly, the centrifugal force has a tendency to push the block in this direction. And hence, there is a frictional force due to centrifugal force in this direction. Remember, we have been asked to find the range of omega. So let's draw this again. So this is the block, this is the center, this is the tangential surface. So we have friction due to weight and friction due to centrifugal force. Higher the value of omega, higher the value of the centrifugal force. So far we can assume that since these two forces are in opposite direction, so there is a net friction force on the block is either in this direction or in this direction. for maximum value of omega, we can assume that the net frictional force is in this direction, omega max. And for the minimum value of omega, we can assume that this is the case of omega max and this is the case of omega min. I hope that makes sense. Take your time to understand this. I'll recap. There is some force of friction due to weight W. And this is fixed because the weight is mg, which is fixed. Omega is our variable here that we are trying to do something with. So as omega goes down, the friction due to centrifugal force goes down, and hence this force starts to dominate. So at the minimum value of omega, we can assume that we will consider the net friction force to be in this direction, which is this case. Similarly, as omega goes up, centrifugal force goes up. The friction due to centrifugal force goes up. So at some point, this force starts to dominate this force, and the net frictional force is in this direction. So this is the case when we'll consider net frictional force in this direction in the case of omega max. So let's analyze the two cases. Case 1, omega max. So let's do the free body diagram again. FBD and frame of reference is block. Again, non-inertial. This is the block. This is the tangential surface. This is theta. And this is the direction of gravity. So this is mg. This is the normal reaction. So this angle is theta. This is m omega square r sine theta. Yes. This angle will be theta as well. And we also discussed that in the case of omega max, we'll consider the friction to be in this direction. So the net frictional force is in this direction. So we can see that since there is no motion in this direction, hence n equals mg cos theta plus, so that is the component of mg in this direction and the component of this in this direction, and of course there is no component of friction in this direction since this angle is 90 degree. So the other component is in the direction opposite to n is m omega square r sine theta times sine theta. So n is mg cos theta plus m omega square r sine square theta. Now next, if we consider the equilibrium in this direction, then F plus mg sine theta will be this component of the centrifugal force. So F plus mg sine theta equals m omega square sine theta times cos theta. M omega square r sine theta times cos theta. Also, F equals mu times n. Remember that mu is a given quantity in the problem. So we can use these three. So we can substitute the value of F and n inside this equation to obtain mu mg cos theta plus mu m omega square r sine square theta plus mg sine theta equals m omega square r sine theta cos theta. By the way, this is the case of omega max, so we can replace omega with omega max in the analysis of this entire case. So omega max So this implies that m cancels out from everywhere, all the terms. This implies that omega max square r times sine theta cos theta minus mu sine square theta equals mu g cos theta plus g sine theta. And hence omega max is g times sine theta plus mu cos theta over r sine theta times cos theta minus mu sine theta to the power 1 by 2. So this is the value of omega max, maximum value of omega to maintain the steadiness of the block. Now let's do case 2 of omega min. Let's do the free body diagram again. So we have center of the sphere, the block of mass m, tangential surface perpendicular to this radius, and there is mg, there is n, this is theta, and omega square r sine theta. And we had concluded that for the case of omega min, we'll have this direction of the resultant net friction. So this is F and this is omega min. So we can analyze similarly to the previous case now. We have n equals mg cos theta plus m omega square r sine square theta. And then we have F equals, this is the equilibrium in this direction. Now if this one is the equilibrium in this direction, now we do equilibrium in this direction, then we get F plus m omega square r sine theta, and this angle is theta. So the component of this in that direction is m omega square sine theta times cos theta equals, and then the component of the weight in the opposite side is mg sine theta. And then the third thing we know is that F equals mu times n. Again, mu is a given quantity. So all of this implies that this is min. All right, so all of this implies that omega min square r times sine theta times mu sine theta cos theta equals g times sine theta minus mu cos theta. Hence, omega min is g times sine theta minus mu cos theta upon r sine theta times mu sine theta plus cos theta to the power half. So the question was, find range of omega so that steadiness is maintained, and we have found the answer that the maximum value of omega is this and the minimum value of omega is this. Thank you.